Welcome to today's video. In this video, we're going to look at the applications of probability generating functions, in particular with respect to the sums of independent random variables. This is the fourth and final series on applications of PGFs. So let's begin, and I'm going to make a claim about probability generating functions and independent random variables. So suppose we have x1, x2, xn are independent random variables. All right, so I've got n random variables, each of them independent of the next. And let's say they have, with probability generating functions, what we'll label them as px1 of z, px2 of z, all the way to pxn of z. And let's define the following. Define S, and I'll call it S, the sum is going to be the sum of all those random variables. Or in shorthand form, we're going to say it's equal to I equals 1 to n of xi. Shorthand form. Here is my claim. The probability generating function of S, which of course we define as the expected value of z to the s, will actually equal the product of all the respective probability generating functions. So this is the shorthand notation. It's the product of I equals n of all the generating functions. But to give you some clarification, that just means the product of px1 of z times px2 of z times ... times probability xn of z. So this is my claim. Now, of course, I want to prove this to you. So, here goes nothing. The probability generating function of S with respect to Z is equal to the expected value of Z to the S, which in this case is the expected value of Z. Now I'm going to re-express S by the definition of what we called it before. It's the sum of x1, x2, x3. So that becomes x1 plus x2 plus ... plus xn in the power there. Now, from here, what we actually note is we've got z to the power of a sum. And we know something by power laws. We know that when you have a sum, or in general, if you have a to the m times a to the n, that is the equivalent of saying a to the m plus n in power notation. The opposite is obviously true. If you have m plus n in the power, you can separate it as a product. So that's what we're going to do here. The zx1 plus x2 plus x all the way to the power of xn, we can rewrite that as the product of z to the power of xi's. Then what is interesting here is that x1, x2, xn are all independent of one another. And one condition of independence is where, say, you have two random variables, x and y, and this symbol here means independent. Where you say have two random variables, and in general, and they're independent, then it follows, the following follows. The expected value of, say, f of x times g of y, right? So if I just, these are just some generic functions, f of x, and some generic function, g of y. That is in fact equal to the expected value of f of x times the expected value of g of y. And this is an important property, right? So if you have independent functions, a product, or independent random variables, sorry, a product of functions of those random variables and taking the expectation is the equivalent of taking the expectation of the two functions independently. And so bringing that back, of course, in context of what we were doing here, this means that we can re-express this expectation as zx1 times the expectation of zx2 times times the expected value of zxn. And of course, now by definition, we know what each of these expectations represent. They represent the respective probability generating functions. So if we now substitute in our probability generating functions, we can now prove that this is in fact the product of I equals n of the xi's, the probability generating functions at xi's, which is my result above. So, very interesting property. Now, this is, of course, a very important property, but let's try to understand how that will actually work in practice with some examples. What we're going to observe is that this property here ultimately allows us to determine the distribution of S if we know x1. So let's take a look at some examples of how that happens. Here's our first example. Suppose each of our xi's, in other words, x1, x2, x3, all the way to xn, all have a Bernoulli distribution, right, with parameter probability of success parameter p. So for I equals 1 to n. And let's say they're all independent random variables. We've got to find the distribution of the sum of those Bernoulli random trials. Well, first thing to begin with is to note that if xi has a Bernoulli distribution with parameter p, then this implies that the probability generating function is given by 1 minus p plus pz. Now, if you haven't seen this before, I encourage you to look at some other videos where I derive this particular probability generating function. But for now, I'm going to take it as given. Now, using our property we had before, we know that the probability generating function of S is equal to the product of I equals 1 of the xi's, the respective probability generating functions of each of those trials. So now it's a matter of substituting the probability generating function we had above into this expression. So that becomes the product of I equals 1 to n of 1 minus p plus pz. And I'll just put brackets around to make it a bit more clear. Now, one thing to note here is that we're going from an index I equals 1 to n. But you'll notice that the function inside the brackets here does not depend on any index I. In fact, it's a constant, really, with respect to the index I. And therefore, when you take a product of I equals 1 to n of a constant, it is the equivalent of multiplying the constant by itself n times. So in other words, you'd have 1 minus p plus z to the n, plus pz, all to the power of n. We're multiplying by itself n times. Now, what you might recognize is that this is the probability generating function of a binomial random variable. And because PGFs are unique, we can say by the uniqueness of PGFs, S must follow a binomial random variable with parameters n and p. And again, if you haven't seen this PGF, I encourage you to look at some other videos where we do show that it is in fact the case that a binomial distribution has this exact probability generating function. But what the main point of this is, given one probability generating function, plugging it into our expression for the sum, we can show that the sum of n independent Bernoulli trials, each with the same probability of success parameter p, is a binomial distribution. And this, of course, is a well-known fact as well. The sum of Bernoullis is a binomial. By very definition, that's what a binomial random variable is, the sum of independent Bernoullis. Great. Let's look at another example. In this example, we have xi, each of our xi variables, is a binomial distribution. Each of them have the same probability of success parameter p, except in this case, the number of trials for each xi is a different value, or not necessarily a different value, but a value which doesn't necessarily have to be the same for each of those I equals 1 to n. Right? First random variable might have 2 trials, the next one might have 5, 6 trials, but they do all have the same probability of success parameter p. And of course, they are independent. That is the one necessary condition for these, for the formula we're going to use to work. Again, we need to find the distribution of the sum. So, in this particular case, what we're going to recall is if xi has a binomial distribution, and it's got parameters mi and p. This implies that the probability generating function, evaluated at z, is now the generating function is 1 minus p plus pz. Now, before we actually saw, you know how it was n, right? That was for a binomial distribution with parameter n. But now we have parameter mi. So this needs to be now mi inside the power, to denote that each xi doesn't necessarily have the same PGF. They have a different PGF dependent on this power. Keeping that in mind, again, we're going to find the probability generating function of the sum, which we said we could use the product of I equals 1 to n of the respective probability generating functions of xi's. Again, we can substitute that product I equals 1 to n of 1 minus p plus pz to the mi. It's here I'll pause and have an aside, because I want us to remind ourselves of a very important power rule. And that is that if you have a power, and then to the power of m, and you multiply that by a to the power of n, in other words, two items have the same base but two different powers, then this is the equivalent of saying a to the m plus n. This is a quite a rudimentary or basic known fact from mathematics from earlier studies, of course. But in the context of this particular product here, what you'll notice is that if I were to expand this product, this would look like 1 minus p plus pz to the power of m1 times 1 minus p plus pz to the power of m2 times times 1 minus p plus pz to the power of mn. Now, the reason I brought up this yellow text over here is because you'll notice we have something similar happening here. We have a base to some power, a base to some power, a base to some power. All of the bases present here are the same. All of the powers aren't necessarily the same, but we know we add the powers all together from this expression in yellow above. So this can be rewritten as 1 minus p plus pz to the power of m1 plus m2 plus plus mn. Or in shorthand form, we can rewrite this as 1 minus p plus pz to the power of, and in shorthand form, we can say I equals 1, the sum of I equals 1, to n of mi, right, inside the nice power. Now, interestingly, we've done as much simplification as possible. Interestingly, this actually still looks like the probability generating function of a binomial random variable. The difference is we don't just have mi as the power, we have the sum of mi's as the power. And so by the uniqueness of PGFs, sorry, I forgot how to spell for a second there. PGFs, you have that S has a binomial distribution with now parameter not mi or m, but rather I equals 1 to n mi's and probability of success parameter p. In other words, the sum of binomials, all with the same probability of success parameter p, is another binomial distribution with probability of success parameter p, except now it is the equivalent of summing up all the trials, the number of trials in each of those binomial random variables. A very interesting property. Let's now take a look at another example to see this result. In this example, we have that each of our xi's for I equals 1, 2, 3, all the way to n have a geometric distribution with probability of success parameter p. And they are, again, independent. That is a very important condition. And we need to find the distribution of their respective sum. Well, again, let's first find the distribution of, say, the single geometric distribution. So if xi has a geometric distribution with probability of success parameter p, this implies that the probability generating function of xi is given by the following. Pz all over 1 minus 1 minus p of z. Apologies, let me rewrite this as just p over 1 minus 1 minus p of z. I'm here going to be using the definition of a geometric random variable, which is the number of failures before the first success, or before a success. That is the definition of the geometric random variable in this case, and this is the PGF that comes out as a result. And again, please, I encourage you to look at other videos in the channel which derive this result. But for now, we'll take it as given. So, the probability generating function of the sum, again, is going to be the product of I equals 1 to n of the individual probability generating function, which in this case is the product of I equals 1 to n of p on 1 minus 1 minus p z. Further to this, we have that the index I there is no mention of the index I in this particular expression or this particular probability generating function. And because of that, when you take a product of the same term n times, it is the equivalent of taking that term 1 on 1 minus 1 minus pz to the power of n, multiplying by itself n times. And what we'll recognize here is that this particular expression actually happens to be the probability mass function of a negative binomial random variable with parameter n and p, with parameters n and p. So, by uniqueness of PGFs, S has a negative binomial distribution with parameters n and p. And the definition of the negative binomial distribution that has this particular PGF is the total number of failures before n successes, which intuitively makes sense because the negative binomial is by definition the sum of geometric and geometric random variables. Some n times when you have one, or the number of failures before one failure, number of failures before one success, sum that up n times, you'll get the total number of times it takes you, or total number of failures before you have n successes. Let's now look at a fourth example. In this particular example, we have a negative binomial random variable with parameters Ri and P for each xi. In other words, each of the xi's have the same parameter of success P, but rather they have a distinct number of successes required before the trials stop. And that, of course, is going to be the case for I equals 1 all the way to n. And again, they're going to be independent random variables. We need to find the distribution of S, which is the sum of x1 plus x2 all the way to xn. Well, firstly, note that if xi has a negative binomial distribution with parameters ri and p, then this tells you that the probability generating function of xi is going to have the value p. Well, it's going to look very similar to the one on above. Well, p 1 minus 1 minus pz, all to the power of ri. In other words, it looks very similar to the PGF that we saw before, except instead of n as the number of trials or number of successes required before termination, you've got ri as the number of successes. Now, because they're independent, this tells us that the probability generating function of the sum is equal to the product of the respective probability generating functions of xi. Now, of course, we can now substitute in our functions that we derive or that we set above. That becomes the product of I equals 1 to n of p on 1 minus pz. Close that to the power of ri. Now I'm going to expand that for us. So the first term when the index is I, or when the index is 1, we end up with r1 as our power, times the next term in the sequence would be 1 minus pz to the power of r2 times ... times, and of course we go all the way up to p on 1 minus pz to the power of rn. And again, we've seen in similar situations where we have the same base, we're multiplying by the same base but a different power. This is the equivalent of taking the base 1 minus pz and adding the powers together plus rn when multiplying, of course. Notice we're multiplying here. Or in shorthand form, we can rewrite this sum up here, r1 plus r2 plus r all the way to rn. We can rewrite that as 1 over 1 minus pz to the power of sum I equals 1 to n of ri in brackets. Now, what I want you to notice here is that the form or the look of the negative binomial, sorry, I should have said negative binomial here with ri and p. The form that we have looks very similar to the form below. Instead of ri, we now have the sum of ri's. That actually tells us that this too is a negative binomial expression. So by the uniqueness of PGFs, what we have here is that the sum is a negative binomial distribution. Now with parameters r equals, or the sum of ri's and probability of success parameter p. In other words, what we've discovered here is that if you have a sequence of negative binomial distributions that are independent, but they all have the same probability of success parameter p, then the sum of those respective negative binomials will also be a negative binomial. A very interesting result. Let's now take a look at our fifth and final example involving the Poisson distribution. In this final example, we have that our xi, each xi, is distributed with a Poisson distribution, but each of the rate parameters is distinct from the next. In other words, each xi at least has a distinct rate parameter. And that's going to be true for I equals 1 through to n. And of course, we're going to note that they are independent. We need to find the distribution of the sum. So firstly, let's find the PGF of xi. So if xi has a Poisson distribution with rate parameter lambda I, this tells us that, in fact, the probability generating function of xi is equal to e to the lambda I z minus 1. Now, of course, I encourage you to view other videos to see why this is the case, but for now we're going to take this as a given result of probability generating functions. Now, the note in, of course, is that now we have lambda I as our particular rate parameter rather than just generic lambda. So, keeping that in mind, because they are independent, the probability generating function of the sum is, of course, equivalent to the product of the respective probability generating functions of the xi. So substituting our expression for the probability generating function gives us lambda I z minus 1. Expanding this term gives us an index of I equals 1. We'll start with gives us lambda 1 z minus 1. Using the next index, we'd get lambda 2 z minus 1 times times all the way e to the negative lambda z minus 1. Now, using our knowledge of powers, we know that when you have the same base multiplied by itself with different powers, that is the equivalent of taking the base and then adding the powers together. Z minus 1 plus plus lambda n z minus 1. Then, of course, we can recognize there's a z minus 1 as a common factor in the summation here, which gives us e to the lambda 1 plus lambda 2 plus plus lambda n times z minus 1. And of course, the final step in this is to simplify the lambda 1 all the way to the plus lambda n, which can be rewritten as the sum of I equals 1 to n of lambda I, and of course still multiplied by z1. And interestingly here, we note that the form or the expression here looks very similar to the former expression here, except instead of sum of lambda i's here, we just have a 1 lambda I. But because they are similar in form, we know that it probably follows a Poisson distribution, in particular, because by uniqueness of PGFs, the sum follows a Poisson distribution, not with rate parameter lambda I, but rather rate parameter as the sum of the lambda i's. In other words, the sum of Poissons is also a Poisson, just with the rate parameter summed up. A very interesting and knowledgeable fact here. So to recap, what we've discussed here today is we've used the fact that the probability generating function of a sum of random variables, in particular independent random variables, is equal to the product of their respective PGFs. This allows us to use the uniqueness of probability generating functions to determine the distribution of the sum. I hope this video was useful to you. Thank you for watching. I hope to see you in the next one.